the discovery that shattered certainty. In 1998, the universe betrayed our expectations. For most of the 20th century, cosmologists assumed they knew its trajectory. The Big Bang had set everything in motion, galaxies flung outward in the initial explosion of creation. Gravity, patient and persistent, would slow that expansion over time. The debate was not whether the universe would decelerate, but by how much. Some predicted a closed cosmos where gravity would eventually reverse the expansion, collapsing everything into a final fiery crunch. Others envisioned an open universe, one that would expand forever, though at an ever-decreasing pace, its galaxies drifting apart more slowly with each passing epoch. Either way, the assumption of deceleration was treated as nearly inevitable, a cosmic certainty. Then came the supernova surveys. Two teams working independently studied distant Type Ia supernovae stellar explosions so bright they serve as standard candles, reliable markers of distance. By measuring their brightness, astronomers could map the rate of cosmic expansion across time. What they found was not deceleration, but its opposite. The faintness of those distant supernovae implied the universe was not slowing down at all. It was speeding up. Galaxies were racing apart faster today than in the past, as though some hidden hand were pushing them outward. The shock was immediate. No existing theory had anticipated such behavior. To reconcile the data, scientists invoked a mysterious force, an energy permeating all of space, acting as a kind of anti-gravity. It was christened dark energy, but the name disguised ignorance. Nobody knew its nature, only its effect, the acceleration of the cosmos. Overnight, the narrative of the universe changed. No longer a story of slowing and collapse, it became one of runaway expansion, with galaxies drifting forever into unreachable isolation. The psychological impact was immense. Humanity had imagined the cosmos as vast but predictable, ruled by gravity's patient hand. The 1998 discovery shattered that certainty. It revealed that the majority of the universe's content is invisible, intangible, and fundamentally mysterious. Dark energy, along with dark matter, now accounts for roughly 95% of reality, an admission that the cosmos we thought we understood is mostly composed of unknowns. More unsettling still was the implication for fate. If acceleration continues unchecked, distant galaxies will slip beyond our horizon, vanishing from view. The universe will not end in fire, but in silence. Stars burning out in isolation, a cosmos expanding into a cold, dark emptiness. The discovery forced us to confront not only new physics, but new existential horizons. What began with faint supernovae became a revelation that the universe is stranger than anyone imagined. The cosmos was not winding down gently. It was racing toward a destiny no one had foreseen. In 1998, we learned that certainty is fragile and that the greatest mysteries are often hidden in the very light we trust to guide us. Dark energy. When the universe's acceleration was first announced in 1998, scientists were left with a profound problem: how to describe a force they could neither detect directly nor explain. The data pointed to something real, something pushing galaxies apart with increasing speed, yet no known particle, field, or mechanism could account for it. Faced with this void of understanding, cosmologists did what humans have always done. When confronted with the incomprehensible, they gave it a name. They called it dark energy. The term was both useful and misleading. Dark suggested invisibility, inscrutability, a phenomenon hidden from our senses and instruments. Energy hinted at a physical force, something measurable, quantifiable, perhaps even harnessable one day. But in truth, the phrase concealed ignorance rather than expressed knowledge. Dark energy was not a theory, not a description, but a placeholder. It acknowledged the effect that the cosmos is accelerating without claiming to understand the cause. History is full of such linguistic placeholders. Early cartographers marked uncharted regions with "Here be dragons," a symbolic way of acknowledging the unknown without defining it. In medicine, diseases once carried names that merely described symptoms: consumption for tuberculosis, dropsy for edema, until deeper causes were discovered. In the same way, dark energy is less a discovery than an admission. We observe its fingerprints, but the hand itself is invisible. This distinction between naming and knowing matters deeply. To name is to domesticate, to place a phenomenon within human language. It gives the illusion of control, but knowing requires more than a label. It requires mechanism, theory, and predictive power. With dark energy, science has achieved the first without the second. The name gives us something to say, but not something to understand. And yet the act of naming is not trivial. Language shapes inquiry. By calling it energy, cosmologists framed the mystery as a physical component of the universe, a measurable entity rather than a metaphysical abstraction. The label directs the questions scientists ask. Is it a constant property of space, like Einstein's cosmological constant, once proposed and then abandoned? Is it a dynamic field that evolves with time, a quintessence whose strength waxes and wanes? Or could it be evidence that our theories of gravity themselves are incomplete? Each hypothesis grows from the soil of that initial name. But the danger lies in mistaking the label for the reality. Too often, dark energy is spoken of as though it were understood, as if it were a substance tucked away, waiting to be bottled. In truth, it remains a cipher, a confession written in scientific shorthand. The name unites scientists in conversation, but it also conceals the radical fact that we do not know what constitutes 70% of the cosmos. We live in a universe dominated by a mystery hidden behind a convenient phrase, philosophically, this tension reveals something about the human condition. We are creatures who name first and know later, who wrap ignorance in language to make it bearable. Dark energy is the modern equivalent of mythic chaos, a word that acknowledges a presence beyond comprehension. It reassures us that the unknown has a place in our lexicon, even if not yet in our theories. Thus, the story of dark energy is not just about physics, but about humility. To name is not to know, and to know may require generations yet to come. For now, dark energy remains less a solution than a reminder that the universe is still filled with mysteries too vast for our current understanding, but close enough to demand our attention. A universe gone rogue. What does it mean to live in a universe that is running away from itself? Before 1998, the cosmic story was one of balance, gravity holding expansion in check, galaxies bound together by the slow tug of inevitability. The image was almost comforting, an ordered universe governed by forces we could describe, perhaps even predict, but the discovery of acceleration shattered that picture. Instead of a cosmos settling into stability, we inhabit one that is fleeing ever faster into distance, a universe gone rogue. This vision unsettles more than physics. It unsettles meaning. Expansion implies separation, not union. Galaxies that once shared a common beginning will one day vanish from one another's sight, pulled so far apart that no signal can bridge the void. In the far future, the night sky itself will empty, stars extinguished, galaxies erased from view. To imagine this is to imagine a cosmos where memory itself fades, where even the universe forgets its origins. Philosophically, the image carries existential unease. A universe accelerating without purpose seems indifferent to coherence, to narrative, to the very idea of home. It does not circle back in cycles, offering the comfort of recurrence. It does not slow toward closure, promising a final reckoning. In collapse, it simply runs, expanding without explanation, without end, as though fleeing from something invisible or fleeing from itself. What does it mean then for us? We are beings who crave connection, pattern, and meaning. We build stories. From beginnings and endings, seek order in chaos, cling to the idea of continuity. Yet the cosmos tells a different story, one of dispersal and disintegration. In such a story, even survival seems fragile, dwarfed by a destiny in which everything familiar dissolves. We cannot grasp acceleration with our hearts, only with our equations, and the result is a kind of cosmic vertigo. And yet, there is also a strange beauty in this disquiet. To exist in a universe gone rogue is to be reminded that we are not its masters. We are witnesses to a mystery far larger than ourselves, inhabitants of a cosmos that will not sit still, that refuses to conform to our need for order. In its flight, the universe reveals its freedom, and in our unease we glimpse our own fragility. Perhaps meaning does not lie in taming the cosmos, but in facing its untamable truth. A universe accelerating into emptiness is terrifying, yes, but it is also magnificent. It reminds us that existence is not bound to human expectation, that reality exceeds the grasp of narrative. To live in such a universe is to stand at the edge of comprehension, humbled by the vastness, unsettled by the trajectory, yet compelled to wonder all the same. Cosmic yardsticks. How do you measure something as vast as the universe? On Earth, distance is tangible. We count steps across a room, miles across a country, kilometers around the globe. Even the moon hanging above us feels measurable in familiar terms, roughly 384,000 kilometers, a number the mind can just about picture. But when astronomers confront galaxies billions of light years away, intuition collapses. Human senses are tuned to horizons, not infinities. To bridge this gulf, science requires yardsticks that stretch beyond imagination. Among the most powerful are type Ia supernovae. These extraordinary events occur when a white dwarf, the dense remnant of a star like our Sun, steals matter from a companion until it reaches a critical mass. At that threshold, it detonates in a runaway thermonuclear explosion. The result is astonishing. A supernova so luminous it can outshine an entire galaxy for weeks. Yet the true power of type Ia supernovae lies not only in their brilliance, but in their consistency. Each one detonates at nearly the same mass, releasing nearly the same amount of energy. In the vast and chaotic cosmos, they are remarkably reliable beacons. Because of this reliability, astronomers can use them as standard candles. By comparing their intrinsic brightness to their observed brightness, they can calculate how far away they are. The principle is deceptively simple. A 100-watt bulb looks bright up close, faint from afar. Measure the apparent brightness and you know the distance. On human scales, the analogy feels obvious. On cosmic scales, it is revolutionary. These stellar explosions become yardsticks stretching across billions of light years, allowing us to chart the universe's expansion with precision. The contrast between human and cosmic scales is almost absurd. We measure our lives in years, our journeys in miles, our memories in generation. Yet type Ia supernovae allow us to measure not lifetimes but cosmic histories, to peer back billions of years, reading the universe's expansion like tree rings, etched into starlight. Where intuition falters, mathematics and light carry us farther than imagination alone could reach. It was through these cosmic yardsticks that the 1998 revelation arrived. By mapping the distances to dozens of type Ia supernovae, astronomers expected to see evidence of a slowing universe. Instead, the data revealed acceleration. What appeared as faintness was not distance alone, but the signature of galaxies receding faster than anticipated. The humble principle of brightness and distance became the lever that pried open the deepest mystery of modern cosmology. In this way, type Ia supernovae embody the paradox of science. Fragile stars dying in violence become the instruments by which we measure eternity. Their explosions echo across time, whispering to us not only about where they are, but about how the universe itself is changing. Against the backdrop of human scales, they remind us how small we are. Yet against the backdrop of cosmic scales, they remind us of our capacity to understand. The cosmic microwave background's hidden message. Long before telescopes glimpsed galaxies racing apart, the universe left behind another kind of testimony, a faint afterglow known as the cosmic microwave background, or CMB. Discovered in 1965, this relic radiation is the oldest light we can see, released roughly 380,000 years after the Big Bang, when the cosmos cooled enough for atoms to form and photons to travel freely. To human eyes, it would appear as uniform darkness, but to sensitive instruments it is a nearly perfect glow, stretched into microwaves by billions of years of expansion. It is, in a sense, the baby picture of the universe, a portrait of its earliest moments frozen into light. At first glance, the CMB seems smooth, almost featureless, yet hidden within its faint irregularities, tiny fluctuations in temperature at the level of millionths of a degree, lies a wealth of information. These subtle patterns encode the distribution of matter and energy in the infant cosmos, seeding the large-scale structures we see today: galaxies, clusters, filaments stretching across space. The CMB became a Rosetta Stone for cosmology, allowing scientists to test theories of inflation, matter content, and the overall geometry of the universe. But the background does more than preserve the past. It also hints at the present. By studying the CMB's minute anisotropies, ripples imprinted across the sky, astronomers can infer how the universe has expanded since that ancient light was released. Just as echoes in a cave reveal the size of the chamber, the CMB's ripples reveal the universe's dynamics. When combined with observations of supernovae and galaxies, the message becomes clear. The expansion is accelerating, and dark energy must be at work. Here lies the paradox. The CMB is a relic, the oldest light we possess, yet it speaks directly to a modern mystery. It was emitted when the universe was young, long before dark energy's influence became dominant. And yet the way that relic light has stretched and distorted on its long journey to us encodes information about dark energy's role in shaping cosmic history. In this sense, the CMB is both ancient and contemporary, a fossil that whispers about the present. Contrast this with our intuitive sense of history. Human relics, fossils, ruins, manuscripts speak only of their own time. A Roman coin tells us about Rome, not about Silicon Valley, but the cosmos works differently. Because light must travel, every ancient photon is a messenger carrying not only its origin but also the imprint of the journey. By analyzing those imprints' patterns of polarization, slight shifts in energy, scientists read not only the universe's birth, but its ongoing acceleration. The CMB has thus become one of the strongest pieces of evidence for dark energy. Without it, acceleration might have been dismissed as a misinterpretation of supernova data. With it, the picture converges. Multiple independent observations pointing to the same unsettling conclusion. The universe is not simply expanding, but doing so under the influence of something invisible, pervasive, and poorly understood. Philosophically, the CMB deepens the enigma. A relic of the first light now encodes the secret of a force shaping the last. The symmetry is haunting, the alpha of the cosmos, pointing toward its omega. The most ancient photons carry signatures of the most modern mystery, uniting, beginning, and end in a single glow. It is as though the universe ensured that even in its infancy, it would leave us clues about its destiny, if only we had the courage to look closely enough. The cosmic microwave background's hidden message. When we look into the night sky, most of what we see is recent. By cosmic standards, stars a few million years old, galaxies billions of years in the making. But hidden beyond them all is a faint glow that predates everything visible, a light older than stars themselves, the cosmic microwave background, or CMB. First detected in 1965 by Arno Penzias and Robert Wilson, this background radiation is the universe's oldest surviving signal, released 380,000 years after the Big Bang. It is not dramatic or dazzling. It is a near-uniform haze, stretched into microwaves by expansion. Yet within that faint glow lies a message more profound than any star could give. The CMB is a relic, the fossil light of a newborn cosmos. At its birth, the universe was a seething plasma where photons scattered endlessly off free electrons, rendering space opaque. Only when atoms formed allowing light to travel freely did the first photons stream outward. Those photons still journey across the cosmos, cooling as space expands, now filling every corner of the sky. To radio detectors, the entire universe hums at just a few degrees above absolute zero. At first glance, it seems smooth, nearly featureless, but this apparent uniformity hides secrets in its delicate irregularities. Tiny fluctuations in the CMB's temperature, measured to millionths of a degree, trace the universe's primordial structure. These ripples reveal the distribution of matter and energy at the dawn of time, the seeds of galaxies and clusters. More remarkably, they also contain imprints of the universe's geometry and expansion history. The CMB is not simply a photograph
of the past, it is a record of the journey from then until now. Each photon carries the signature of the cosmic expansion.
It is here that the shadows of dark energy appear. By comparing the scale of fluctuations in the CMB to the structures we see today, scientists discovered a mismatch. The universe could not have grown into its current state without an extra ingredient, accelerating its expansion. Relic light, in other words, encodes the fingerprints of a modern mystery. Though emitted when dark energy's role was negligible, the CMB photons have been stretched, bent, and scattered during their 3.8-billion-year journey, leaving subtle distortions that betray dark energy's hand. This duality is striking. The CMB is the oldest evidence we can measure, yet it testifies to the newest and most enigmatic force in physics. Relic light points to a modern mystery. The alpha of the cosmos whispers of its omega, where human relics only tell of their owns. Age cosmic relics carry the weight of all time, embedding past and future into a single signal. Philosophically, the message unsettles. The CMB reminds us that beginnings and endings are not separate, but intertwined. The first light of creation contains the echo of eventual dissolution. To study the CMB is to hold eternity's paradox in our hands, that the most ancient glow of the universe also encodes its ultimate trajectory. A faint hiss in the microwave band becomes the cosmos's most profound confession that what we see today is already shaped by what we cannot yet understand. The mathematical imprint. When astronomers uncovered the accelerating expansion of the cosmos, they did not begin with new mathematics. Instead, they turned back to a century-old equation, Einstein's general relativity. At its core, general relativity describes how matter and energy curve space-time, and how that curvature dictates the motion of matter and light. It is a theory of gravity, elegant and relentless, tested in countless experiments, but woven into its fabric lies a term Einstein himself once introduced, then abandoned: the cosmological constant. With the discovery of dark energy, this forgotten symbol returned from exile, carrying new weight and deeper mystery. Einstein first added the cosmological constant in 1917, not out of evidence, but out of desire. At the time, the prevailing assumption was that the universe was static, neither expanding nor contracting. Yet his equations suggested otherwise. Left to themselves, they implied a dynamic universe, unstable under gravity. To counter this, Einstein inserted an additional term, a kind of repulsive force, finely tuned to balance gravity's pull and hold the cosmos steady. It worked mathematically, but it was fragile, a knife-edge balance easily disturbed. When Hubble later showed the universe was indeed expanding, Einstein abandoned the constant, calling it his greatest blunder. For decades, the cosmological constant lay dormant, a relic of an outdated model. Then came 1998. Observations of Type Ia supernovae revealed not a slowing cosmos, but an accelerating one. Suddenly, the very kind of repulsive force Einstein had introduced, dismissed as unnecessary, was required again. To explain dark energy, scientists revived the cosmological constant, denoted by the Greek letter lambda. The same symbol Einstein once regretted became the simplest explanation for the most shocking discovery in modern cosmology. In this form, lambda represents a uniform energy density filling space itself, an intrinsic property of the vacuum. Unlike matter or radiation, it does not dilute as the universe expands. Instead, its effect grows more dominant over time, steadily accelerating cosmic expansion. Mathematically, it fits the data with striking elegance. Insert lambda into Einstein's equations, and the accelerated expansion appears naturally. In fact, the cosmological constant now defines the standard model of cosmology known as LCDM, in which dark energy, lambda, and cold, dark matter, CDM, govern the universe's large-scale evolution. Yet elegance does not mean understanding. The cosmological constant explains acceleration, but only as a symbol, not as a mechanism. Quantum field theory predicts vacuum energy should exist, but its calculations overshoot by an astonishing 120 orders of magnitude. The so-called cosmological constant problem is among the greatest puzzles in physics. Why is the vacuum energy so small yet not zero? Why does it take precisely the value needed to shape cosmic history? The mathematics is simple. The implications are staggering. Here lies the paradox of dark energy's mathematical imprint. On the chalkboard, lambda is just a symbol, a constant with no moving parts. In reality, it dominates the fate of the cosmos, dictating whether galaxies drift into eternal isolation or collapse into fiery rebirth. A single term in Einstein's equations carries within it the power to reshape destiny. Philosophically, the cosmological constant is both humbling and haunting. It reveals how equations can anticipate truths long before observation confirms them, how mathematics can see deeper than intuition. Yet it also underscores our ignorance. We can write the symbol, solve the equations, even model the universe's future, but we cannot say what lambda is. Einstein's blunder became our foundation, but it remains a placeholder for mystery. In the end, the cosmological constant is less a solution than a reminder that mathematics can reveal the contours
of reality, but reality still resists full comprehension.
A single Greek letter binds together the birth of galaxies, the flight of light, and the destiny of time itself. Einstein's biggest blunder reconsidered. In 1917, Albert Einstein faced a dilemma. His newly minted general theory of relativity described a universe in motion, dynamic, unstable, either expanding or contracting under the weight of its own gravity. Yet Einstein, like most of his contemporaries, assumed the cosmos was eternal and static. To force his equations to match that assumption, he introduced a new term, the cosmological constant, represented by the symbol lambda. This mathematical addition acted like a repulsive force, balancing gravity's pull and holding the universe steady. At first, the fix seemed clever, even elegant, but it was fragile. A slight imbalance would send the universe drifting outward or collapsing inward. When Edwin Hubble revealed in 1929 that the universe was indeed expanding, the need for lambda evaporated. Einstein reportedly lamented the addition, calling it his greatest blunder. The cosmological constant became a cautionary tale, proof that even genius could bow too heavily to assumption. For decades, physicists treated it as an embarrassment, a symbol of unnecessary complication. Then came 1998. Observations of distant supernovae revealed not a slowing universe as expected, but an accelerating one. Galaxies were fleeing apart faster with time, as though some hidden repulsion pervaded the cosmos. To account for this, scientists reached once again for Einstein's discarded constant. Suddenly, the blunder was reborn as necessity. What Einstein had introduced to preserve stasis now explained runaway expansion. His error became prophecy. The irony is profound. What Einstein abandoned as unnecessary is today central to cosmology. The standard model of the universe, known as LCDM, takes its name directly from the constant he regretted. Lambda now represents dark energy, the mysterious force driving acceleration and comprising nearly 70% of the cosmos. Without it, our equations fail to describe reality. Einstein's mistake is modern science's cornerstone. And yet, the tension remains. Did Einstein truly blunder, or did he glimpse something deeper than he realized? His constant solved the wrong problem, but in doing so, it anticipated the right mystery. Perhaps his regret was premature, his blunder less a misstep than an accidental discovery whose meaning took a century to unfold. Philosophically, the story reveals both the power and the peril of mathematics. A symbol born from assumption became the key to describing the universe's fate. What was once a patch is now a window into the unknown. But the constant remains enigmatic. It explains acceleration in equations, yet its physical nature eludes us. In reviving Einstein's discarded term, we admit that even our greatest minds stumble into truths they cannot fully comprehend. Thus, Einstein's blunder is reconsidered. It is no longer just a mistake, but a reminder that error and insight often share the same line of chalk. Vacuum energy and the quantum catastrophe. If Einstein's cosmological constant provides the mathematical shorthand for dark energy, quantum field theory attempts to supply its physical meaning. At first glance, the marriage seems natural. According to modern physics, even empty space is not truly empty. The quantum vacuum teems with fleeting particles, pairs that wink into existence and annihilate in unimaginably short timescales. These fluctuations are not speculation. Their effects are measurable in laboratories, where they produce tiny forces and shifts in energy levels. If the vacuum seethes with activity, it seems reasonable to assume that this restless energy contributes to the expansion of the universe. The logic is straightforward. General relativity says energy curves space-time. Quantum field theory says the vacuum contains energy. Put the two together and the cosmological constant becomes nothing more than vacuum energy written into Einstein's equation. Dark energy, in this picture, is simply the pressure of the vacuum itself, pushing space apart. Elegant, persuasive, almost inevitable. But when physicists tried to calculate the numbers, elegance collapsed into absurdity. The predicted value of vacuum energy derived from summing the contributions of all possible quantum fields turned out to be catastrophically large. Depending on the details, the result overshoots observation by a factor of 120. To put this in perspective, it is often described as the worst prediction in the history of science. The discrepancy is so vast it defies analogy, like predicting the height of Mount Everest and finding your calculation taller than the visible universe. And yet, the cosmos does accelerate, just not at that impossible scale. Observations of supernovae and the cosmic microwave background reveal a vacuum energy density that is real, but astonishingly small enough to push galaxies apart, but gentle compared to quantum theory's explosive estimate. Why is the vacuum energy not zero, yet not catastrophically large? Why is it precisely the tiny value that shapes cosmic history without instantly ripping it apart? This puzzle is known as the cosmological constant problem, and it is arguably the deepest rift between quantum mechanics and general relativity. The clash exposes a profound mismatch between two otherwise triumphant theories. Quantum field theory governs the microscopic, explaining particle interactions with exquisite accuracy. General relativity governs the cosmic, mapping the dance of planets, stars, and galaxies. Each is tested to precision, yet when combined at the level of vacuum energy, they diverge wildly. It is as though two master musicians, flawless in solo performance, produce only noise when asked to play. Together. Philosophically, the catastrophe carries weight. It reveals that our most trusted theories, however elegant, may be incomplete. Naming vacuum energy does not mean understanding it. We can calculate its effects in laboratories, we can measure its imprint across the sky, but we cannot reconcile its scale with the mathematics of the cosmos. The discrepancy is not a small error, but a yawning chasm, a reminder that human knowledge still rests on provisional ground. Some propose radical solutions. Perhaps quantum fluctuations cancel out through hidden symmetries, leaving only a residue. Others suggest our equations must be revised at the deepest level, that dark energy is not vacuum energy at all, but a sign of new physics waiting to be discovered. Whatever the answer, the catastrophe underscores humility. For all our equation and instruments, the universe still guards its secrets, reminding us that even the void is not empty, but an enigma, the constant that refuses to stay. Constant. When cosmologists revived Einstein's cosmological constant to explain acceleration, they assumed it was just that, constant, a uniform energy density filling space, unchanging across both distance and time. This view is elegant, simple, and remarkably successful at matching observations. The LCDM model, where lambda represents the constant and CDM stands for cold, dark matter, remains the standard framework of cosmology. But the universe is rarely so obliging. Increasingly, scientists ask, what if dark energy is not fixed but shifting? What if the constant refuses to stay constant? The suspicion arises from both theory and observation. Theoretically, there is little reason why vacuum energy should remain perfectly steady. Quantum fields can evolve, scalar fields can roll, and hidden forces may change their influence as the universe matures. If dark energy is tied to such a field, then its strength could wax and wane rather than remain frozen. In this scenario, cosmic acceleration would not be a permanent fixture but a phase, potentially altering the ultimate fate of the universe. Observationally, hints of variation occasionally appear in the data. Measurements of distant supernovae, the cosmic microwave background, and large-scale galaxy surveys sometimes show subtle tensions, small discrepancies that might suggest dark energy has evolved across billions of years. Most results still align with a constant value, but the margins of error leave room for doubt. Even the possibility unsettles the comforting neatness of LCDM, replacing certainty with dynamism that if dark energy changes, the consequences are profound. A constant lambda predicts an eternal acceleration with galaxies drifting into darkness forever. But a variable dark energy could reverse course. If it grows weaker, expansion might slow, opening the possibility of a more stable cosmos or even eventual collapse. If it grows stronger, expansion could accelerate catastrophically, tearing galaxies, stars, and atoms apart in a so-called Big Rip. Each scenario carries not only different physics, but different existential implications for the meaning of cosmic time. Philosophically, this uncertainty reminds us that permanence may be an illusion. We long for constants, for unchanging truths to anchor understanding. Yet even the cosmos may resist constancy, offering instead a universe defined by change at every scale, from stars that burn out to laws that evolve. Dark energy may not be a static backdrop, but an actor in its own right, shifting character as the play unfolds. In questioning whether the constant stays constant, we confront the possibility that the universe itself is less rigid than we imagined. Its acceleration may not be a fixed decree, but a story still in motion. And like all stories in progress, it leaves us suspended in mystery, wondering what the next chapter will bring. The Hubble tension. At the heart of cosmology lies a deceptively simple question. How fast is the universe expanding right now? The answer is encoded in a number called the Hubble constant, or H0, named after Edwin Hubble, who first showed that galaxies recede from us with speeds proportional to their distances. Measuring H0 should, in principle, be straightforward. Observe how quickly galaxies move apart, compare it to their distance, and derive the expansion rate. Yet in recent years, a startling contradiction has emerged. Depending on how and when we measure the universe, we get different answers. This conflict, known as the Hubble tension, has become one of the most pressing mysteries in cosmology. The first approach to H0 begins with the early universe. By analyzing the cosmic microwave background, CMB, the relic light from 380,000 years after the Big Bang, scientists can extrapolate forward using the laws of physics. The Planck satellite, which mapped the CMB with exquisite precision, delivered a value for H0 of about 67 kilometers per second per megaparsec. This means that every megaparsec of space, roughly 3.26 million light-years, expands by 67 kilometers per second. This number fits beautifully within the LCDM model, the reigning framework that combines dark matter, dark energy, and Einstein's equations into a coherent whole. The second approach, however, looks not at the early universe, but at the present. 1. By using cosmic yardsticks such as Type Ia supernovae and Cepheid variable stars, astronomers can directly measure the distances and recession speeds of galaxies nearby. This method bypasses assumptions about the early cosmos, instead offering a late universe snapshot. The results are strikingly consistent. They point to a higher H0, around 73 or 74 kilometers per second per megaparsec. The discrepancy is small in absolute terms, but immense in scientific significance. The two methods do not overlap within their uncertainties. Thus arises the tension. Early universe physics insists on one number, while late universe observations insist on another. Both approaches are robust, refined by decades of improvements, and cross-checked by independent teams. Both are supported by elegant data, yet they refuse to agree. In science, such stubborn disagreement is not noise, it is signal, a hint that something fundamental may be missing. Several possibilities are on the table. One is that hidden systematic errors still lurk in the data. Perhaps Cepheid calibrations are flawed, or subtle biases remain in the CMB analysis. Another is that new physics is required, that the universe between its early and late stages behaves in ways not captured by the standard model. Speculative proposals include exotic particles that altered the expansion history, or early episodes of dark energy that evolved differently than expected. Each hypothesis underscores the tantalizing possibility that the Hubble tension is more than a nuisance. It may be a clue to deeper laws. Philosophically, the conflict reflects the limits of certainty in cosmology. For decades, scientists spoke of a precision cosmology, a field where the universe's parameters were pinned down to decimals. Yet the Hubble tension reveals cracks in that confidence. It reminds us that even with our finest instruments and grandest models, the cosmos can still surprise us. Naming a constant does not mean fixing it forever. Like dark energy itself, the expansion rate may carry complexities we have yet to imagine. The Hubble tension is thus more than a numerical disagreement. It is a mirror of our situation as seekers, caught between early light and present galaxies, between relic signals and living stars. Somewhere between past and present, the universe resists reconciliation, reminding us that its story is not yet fully told. The cosmic jerk. For decades, cosmologists spoke of the universe's expansion as if it were a smooth, continuous process, galaxies gliding apart under the steady influence of gravity and later, dark energy. The equations of general relativity, once combined with the cosmological constant, produce a graceful narrative, a cosmos that either slows, accelerates, or coasts, but always in a predictable, monotonic way. Yet recent evidence suggests the universe's story may not be so tidy. Instead of a smooth expansion, the cosmos may have experienced sudden changes in pace, what scientists have come to call cosmic jerks. The term is informal, almost playful, but the idea is profound. A jerk in physics is the derivative of acceleration, a change in how quickly acceleration itself changes. Translated into cosmology, it means the universe's expansion rate may not follow a simple curve but could shift dramatically over time. One such moment is already established. Billions of years ago, cosmic expansion slowed under the pull of gravity, only later to reverse course as dark energy took over, driving acceleration. This transition from deceleration to acceleration was itself a kind of cosmic jerk, a turning point etched into the fabric of history. But what if there were others? Recent analyses of supernova data, large-scale structure surveys, and baryon acoustic oscillations suggest that cosmic acceleration may not be as steady as once believed. Some studies hint at periods where dark energy's influence might have fluctuated, altering the rate of expansion in subtle but noticeable ways. Instead of a single, eternal cosmological constant, the universe could be governed by a more dynamic, shifting energy component. These hints remain tentative, but they raise an unsettling possibility that the cosmos is messier, more irregular than the elegance of our equation suggests. This tension between theory and observation is familiar. Elegant models appeal because they compress complexity into symmetry, making the universe intelligible. Einstein's relativity, with its clean geometry, is a triumph of such beauty. The cosmological constant, too, has a certain simplicity, a single parameter explaining acceleration. But nature is under no obligation to be simple. The cosmic jerk challenges us to consider that reality may be irregular, punctuated by shifts and transitions rather than smooth arcs. Philosophically, the notion unsettles our preference for order. Humans long for continuity, for narratives that flow without rupture. A jerking universe prone to sudden changes in pace reflects a cosmos less like a graceful symphony and more like jazz, unexpected, improvisational, sometimes dissonant. It forces us to imagine cosmic time not as a smooth river but as a turbulent current, eddying and accelerating in unpredictable rhythms. If true, the implications are immense. A fluctuating expansion rate could signal that dark energy is not a constant at all, but a dynamic field quintessence, phantom energy, or something stranger still. Each model implies different cosmic futures, universes that rip apart, fade gently, or cycle through epochs of change. In this view, the acceleration we measure today is only one chapter in a more complex story, one that could surprise us again with future jerks. Ultimately, the cosmic jerk reminds us of the humility required in cosmology. Our models, however elegant, are approximations of a reality that may resist smooth description. Just as ancient astronomers once imagined planets moving in perfect circles, only to discover their true paths were ellipses, we may discover that our elegant expansion curves conceal a more jagged truth. The universe, it seems, may prefer messiness to perfection, leaving us to reconcile beauty with reality in the equations of the cosmos. Dark energy in flux. If dark energy were truly a cosmological, constant, unchanging, uniform, and eternal cosmology might rest on firmer ground. But cracks in the neatness of LCDM have inspired scientists to wonder, what if dark energy is not constant at all? What if it is dynamic, shifting in strength across time? This idea has given rise to speculative models that recast dark energy, not as a fixed property of space, but as a cosmic fluid or field evolving alongside the universe itself. One such proposal is quintessent. Unlike the static cosmological constant, quintessence imagines dark energy as a scalar field, something akin to the Higgs field that rolls slowly down a potential energy curve. Its influence changes over cosmic history, sometimes weaker, sometimes stronger, subtly adjusting the rate of expansion. In this model, today's acceleration could be temporary, destined to diminish in the future, leading to a universe that coasts or even recollapses. Quintessence has a poetic appeal. It paints dark energy not as a frozen backdrop, but as a living participant in the cosmic drama, its character shifting as epochs unfold. But the possibilities grow stranger. In another family of models, dark energy, could be more extreme than a cosmological constant. This is known as phantom energy. If quintessence is gentle, phantom energy is feral. Its density increases as the universe expands, feeding on growth instead of fading with it. Left unchecked, phantom energy could accelerate expansion so violently that it eventually tears apart galaxies, stars, planets, even atoms themselves in a cataclysm called the Big Rip. In that future, the cosmos does not fade into quiet isolation, but ends in a storm of disintegration, every structure destroyed by the relentless pull of an ever-strengthening force. Between quintessence and phantom energy lies a spectrum of possibilities. Some theories suggest oscillating fields where dark energy waxes and wanes like a cosmic tide, producing alternating eras of faster and slower expansion. Others propose interactions between dark energy and dark matter, where the two invisible components of the universe exchange energy like dancers, shaping cosmic evolution in tandem. Each scenario departs from the simplicity of Einstein's lambda, replacing elegance with dynamism and uncertainty. Observations so far remain inconclusive. Current data still align most neatly with a constant cosmological term, but the margins leave room for evolution. Slight tensions between early and late universe measurements, the infamous Hubble tension fuel speculation that dark energy might be slipping from constancy into flux. If so, the universe may not have one fate, but many, its trajectory dependent. On the hidden physics of this mysterious force. Philosophically, these models reveal our discomfort with permanence. The idea of a constant suggests stability, but also finality, a mystery neatly packaged, perhaps too neatly. A dynamic dark energy, by contrast, restores uncertainty. It implies that the cosmos is still unfolding in ways we cannot predict, that its laws are more like processes than decrees. The universe becomes less a finished equation and more an evolving story, written in chapters of shifting expansion. Dark energy in flux is speculation, yes, but speculation rooted in the profound recognition that constancy may be an illusion. If quintessence is true, the universe could one day slow its runaway flight. If phantom energy reigns, everything may end in shreds. Both possibilities remind us that our cosmic fate is still unwritten, governed by a force we do not yet understand. In seeking its nature, we are not just predicting the future, we are glimpsing the fragility of everything we call real. Maybe gravity is wrong. When faced with mysteries like dark matter and dark energy, one possibility is that we have discovered new ingredients of the cosmos. Another possibility is more unsettling. Maybe our understanding of gravity itself is incomplete. From Newton to Einstein, gravity has been reimagined before. Why not again? Newton's theory worked beautifully for centuries, describing falling apples and orbiting planets with elegant precision. Yet, at cosmic scales, it faltered. Mercury's orbit drifted in ways Newtonian physics could not explain. Light, massless in Newton's system, was inexplicably bent by the sun. Enter Einstein, who replaced Newton's invisible force with the geometry of space-time itself. General relativity solved Mercury's puzzle, predicted gravitational waves, and became one of the most rigorously tested theories in science. But even Einstein's framework, as majestic as it is, may not be the final word. Consider dark matter. For decades, galaxies have appeared to rotate faster than visible mass allows. The standard fix has been to invoke invisible matter, but an alternative is that gravity weakens differently at large scales. This idea underlies modified Newtonian dynamics, MOND, which tweaks Newton's equations at low acceleration. MOND explains galactic rotation curves without unseen mass. Though it struggles at larger cosmological scales, still it reminds us that perhaps we are too quick to add invisible ingredients when the recipe itself might need revision. More sophisticated alternatives arise within general relativity's own framework. FR, gravity, for example, modifies Einstein's equations by replacing the simple curvature term, R, with more complex function. These modifications can mimic the effects attributed to dark energy, producing cosmic acceleration without invoking a mysterious new force. Other theories, like scalar tensor models or massive gravity, similarly adjust the rules, bending geometry in ways that could eliminate the need for dark energy altogether. Yet every new proposal faces the same challenge: consistency. General relativity has passed every local test, with flying colors from the bending of starlight to the timing of pulsars. Any alternative must match Einstein's successes while explaining phenomena he could not. To date, none have achieved this balance fully. Either they explain galaxies but fail with cosmology, or they explain expansion but falter with solar system precision. Gravity, it seems, resists easy reinvention. Philosophically, the possibility is humbling. Humanity has twice revolutionized its picture of gravity, first with Newton's invisible force, then with Einstein's curving space-time. Both were once unimaginable. Both are now foundational. Could we be on the brink of a third revolution? Perhaps the anomalies we ascribe to invisible matter and energy are not new substances, but signs that our equations describe only part of the story. If so, the greatest mystery of the cosmos may not be hidden matter or exotic energy, but gravity itself, still waiting to be understood. Large-scale cosmic structures. When cosmologists speak of the universe's expansion, they often rely on the assumption that, on the largest scales, matter is smoothly distributed. This simplification, called the cosmological principle, treats the cosmos as homogeneous and isotropic, meaning the same everywhere and in every direction. It allows the complex web of galaxies, clusters, and voids to be averaged into a simple fluid whose expansion can be neatly described by Einstein's equations. But what if that picture is misleading? What if the universe's clumpiness, its vast filaments of matter and yawning cosmic voids creates the illusion of acceleration? The idea arises because light does not travel through a smooth universe. Photon from distant galaxies thread their way through a labyrinth of structure, pulled and bent by the gravity of clusters stretched across empty voids. These distortions can affect how we perceive distance and brightness, the very measurements used to infer cosmic acceleration. In principle, if the universe is sufficiently uneven, the apparent dimming of distant supernovae could be an artifact, not a sign of dark energy, but a trick of perspective shaped by cosmic structure. This speculation is not baseless. On small scales, we know structure matters. Galaxies rotate differently depending on their environment. Clusters lens light in dramatic arcs. Voids produce measurable effects on cosmic microwave background photons through what is called the integrated Sachs-Wolf effect. Extend this reasoning to the largest scales, and one can imagine that the cosmic web itself, the grand tapestry of filaments and voids spanning hundreds of millions of light years, might alter our interpretation of expansion. In this view, the contrast is stark. The smooth universe of equations versus the clumpy reality of observation. A smooth cosmos gives us elegant models, tidy parameters, and the need for dark energy. A clumpy cosmos resists such simplicity. It suggests that what looks like acceleration may instead be uneven growth, our measurements skewed by the inhomogeneities we average away. Yet the evidence so far complicates the alternative. Careful simulations of large-scale structure combined with precision surveys suggest that clumpiness alone cannot fully account for the observed acceleration. The supernovae, the cosmic microwave background, and baryon acoustic oscillations all point toward a consistent story of real acceleration. The distortions caused by cosmic inhomogeneities exist, but they appear too small to mimic the vast effect we attribute to dark energy. Still, the possibility remains philosophically potent. It forces us to confront the limits of our assumptions. The cosmological principle is not proven, it is a working hypothesis. We look at the visible universe, extrapolate smoothness on the largest scales, and build models accordingly. But the cosmos has repeatedly revealed itself to be messier than expected. The very idea of dark matter arose from clumpy galactic rotation curves. Why should we assume dark energy cannot be another artifact of overlooked structure? If uneven, distribution truly explains acceleration. it would represent a profound reframing. Instead of invoking a mysterious new energy-filling space, we would discover that the universe's complexity, its web of filaments, its cavernous voids, was enough to deceive us. Expansion would no longer be a smooth, runaway process, but a patchwork of regions evolving differently, stitched together into an apparent whole. The irony is striking. Humanity seeks simplicity, but the cosmos may offer only complication. Whether or not clumpiness explains acceleration, the debate reminds us that elegance is not truth. A smooth universe is easier to calculate, but the real one may be irreducibly tangled, a vast, cosmic web that resists reduction, leaving us to wonder whether acceleration is a property of space itself or a mirage born of its unevenness. Dark energy. As mirage, what if dark energy is not a thing at all, but a mirage of our interpretation? Science advances not only through discovery, but through correction, by realizing that what once appeared profound was in fact a misunderstanding. History is full of such lessons. The canals on Mars, once thought to signal intelligent life, turned out to be optical illusions. Phlogiston, once believed to explain combustion, dissolved into nothing when chemistry matured. The ether, imagined as the medium of light, evaporated with relativity. Might dark energy someday join this list, less a force of nature than a reflection of our own conceptual errors? The thought is unsettling because dark energy feels so solid in modern cosmology. It dominates our equations, shaping predictions of the universe's fate. Yet its presence is inferred, not directly observed. We see distant galaxies accelerating away. We measure faint supernova. We analyze relic radiation. And from these effects, we conclude something unseen must exist. But inference is fragile. If our assumptions about gravity, geometry, or cosmic structure are even slightly flawed, the entire edifice of dark energy could collapse into illusion. Philosophically, this it
raises a deeper caution. We mistake naming for knowing.
By calling it dark energy, we clothe ignorance in the language of certainty. The name reassures us that a placeholder is an explanation, when in truth it may be a signpost of confusion. If dark energy is a mirage, then its greatest contribution may not be physical, but epistemological, a reminder of how easily even the sharpest minds can be misled by appearances. This does not diminish science. It strengthens it. A mirage is not meaningless, it reveals the limits of perception, just as shimmering water on the horizon tells us something about light and heat. A false cosmological discovery still teaches us about method and humility. If dark energy proves illusory, it will not be a failure but a correction, a refinement in our attempt to read the cosmos honestly. And perhaps that is the real lesson. The universe is vast and strange, and our tools are finite. To misinterpret is
inevitable. To revise is progress.
Dark energy may indeed be real, a profound force woven into the fabric of existence, or it may be a shadow of our own misunderstanding, destined to vanish under clearer theories. Either way, its role endures not as certainty, but as the latest reminder that every discovery carries the possibility of illusion, and that truth is found not in clinging to what we see, but in questioning whether we see it rightly. Eternal expansion and heater. If dark energy is real and unchanging, then the universe's future seems written in chilling clarity. Expansion will not slow, it will accelerate forever. Galaxies, once gravitationally bound neighbors, will drift apart until even the closest become unreachable. Over unimaginable timescales, the cosmos will thin into isolation, and with it comes the bleakest forecast of all, the heat death of the universe. The term is misleading. It suggests fire and violence, but in truth it means the opposite: silence, stillness, and decay. Heat death is the inevitable consequence of the second law of thermodynamics, which dictates that entropy, the measure of disorder, always increases. As stars burn their fuel, as black holes evaporate, as galaxies scatter, the universe moves toward maximum entropy. In that state, all gradients vanish. No heat flows, no energy differences exist, and without differences there can be no work. Life, structure, even time as we understand it, depends on contrasts: light against dark, hot against cold. Heat death erases them all. The contrast with our present universe could not be starker. Today, stars blaze with vitality, forging elements in their cores, scattering brilliance across the void. Galaxies cluster in luminous webs, planets orbit with energy, and life, at least on Earth, thrives in the flux of heat and light. The cosmos is vibrant, dynamic, almost overflowing with creation. To imagine that this exuberance will one day dissolve into uniform cold is to confront the deepest melancholy of physics. The timescales are staggering. Stars, like our sun, will shine for billions of years, but eventually even the longest-lived red dwarfs will burn out. White dwarfs will cool into black husks. Neutron stars will fade, and black holes will evaporate. Over unimaginable spans of time, the galaxies will darken, leaving only faint embers scattered across expanding emptiness. The universe will not end in cataclysm, but in exhaustion. It will not collapse into fire, but spread into silence. A once luminous cosmos becomes a graveyard of entropy. Philosophically, heat death embodies a terrifying vision of eternity. An infinite expansion strips the universe not only of light, but of meaning. We imagine progress, cycles, renewal, but in a heat-death future, there is only decline toward uniformity. Existence becomes less a story than a fade-out, with no climax, no rebirth, only the quiet dissolution of possibility. It forces us to ask, what does it mean to live in a universe whose ultimate destiny is emptiness, and yet there is a strange dignity in this doom? If the laws of thermodynamics dictate entropy's triumph, then our present moment becomes more precious, not less. Against the backdrop of eternal cold, the fleeting vitality of stars is extraordinary. The fact that galaxies shine, that planets form, that life emerges, all of it is a miracle of low entropy, a brief window when complexity could flourish. To recognize its transience is to recognize its value. Thus, the vision of heat death is bleak, but also clarifying. The stars blaze brighter, knowing they will not last. Our awareness itself becomes remarkable, a flicker of meaning in the entropy tide. If eternal expansion leads only to cold silence, then the act of wonder here and now
is not diminished but exalted.
For in a universe destined for stillness, to feel awe at its vitality is the greatest defiance we can offer. Big Rip scenarios. If eternal expansion paints a picture of slow fading, the Big Rip offers the opposite, a violent, catastrophic end to everything. This scenario arises if dark energy is not constant but of the more exotic phantom variety, where its density grows stronger as the universe expands. Instead of thinning out, phantom energy feeds on expansion, amplifying itself in
a runaway cascade.
The result is cosmic acceleration gone feral, an unstoppable tearing that spares nothing, not even the smallest bonds of matter. The progression of doom unfolds in stages. First, galaxies drift apart at accelerating speeds, severing the cosmic web. Structures that once defined the universe, clusters, filaments, superclusters, unravel into lonely fragments. Next, gravity itself is overwhelmed. Galaxies can no longer hold themselves together. The Milky Way dissolves into scattered stars. In time, even stars are torn from their planets, planetary systems dismembered by a force stronger than any orbital bond. But the Big Rip does not stop at the grand scale. As phantom energy intensifies, it invades the intimate realm of matter. Stars themselves are shredded, their plasma ripped apart faster than nuclear fusion can bind it. Planets split, mountains collapse into atoms, and finally, even atoms succumb. Electrons, once bound to nuclei by the electromagnetic force, are wrenched away. Molecules, cells, consciousness, all reduced to subatomic shreds, and then those too are torn into nothing. The very fabric of space-time stretches to annihilation. The contrast is staggering. We look at the cosmos today and see majesty galaxies spinning in elegant spirals, nebulae glowing like stained glass, clusters spanning millions of light years. Yet in the Big Rip vision, all that beauty is temporary, destined for violent annihilation. No slow dimming, no quiet fading, but a crescendo of destruction, ending not in silence, but in rupture. Where heat death whispers, the Big Rip screams. The timescale depends on the exact nature of phantom energy. If its density is only slightly stronger than a cosmological constant, the end lies trillions of years away. But if its value is more extreme, the timeline shortens dramatically, perhaps to billions or even millions of years. In such scenarios, the countdown to annihilation is already ticking, every galaxy's flight a harbinger of deeper disintegration. To come, philosophically, the Big Rip unsettles in a different way than heat death. Heat death robs us of future meaning through endless silence, but at least it grants time vast spans in which stars and life might flourish. The Big Rip, by contrast, is violent certainty, no future, only destruction. It reframes the universe, not as a stage for endless stories, but as a drama with a fixed and catastrophic finale. To imagine existence under its shadow is to feel the fragility of everything we hold dear. And yet, there is awe even here. The very idea that cosmic acceleration could one day dismantle galaxies and atoms speaks to the astonishing power hidden in the vacuum of space. It reveals a universe that is not only majestic, but dangerous, a cosmos whose beauty is matched by its capacity for annihilation. To contemplate the Big Rip is to confront the truth that reality is not designed for our comfort, but for its own inexorable unfolding. If the heat death envisions eternity's stillness, the Big Rip envisions eternity's violence. Both remind us that our universe is finite in its hospitality and that meaning must be made not in some imagined forever, but in the fragile and luminous now. Cycles and rebirth. Not every vision of cosmic destiny ends in silence or annihilation. Some theories suggest that dark energy, rather than spelling doom, could be the engine of renewal. In these models, the universe does not march toward a final heat death or Big Rip, but instead enters cycles of collapse and rebirth, an eternal series of beginnings woven into the very fabric of time. This idea is not entirely new. Ancient mythologies often imagined time as circular, with ages repeating endlessly, worlds destroyed and remade. In modern cosmology, cyclic models give that intuition scientific form. If dark energy is not constant but evolves, it could one day reverse its role. Instead of accelerating expansion forever, it might weaken, allowing gravity to regain dominance, pulling the universe inward toward a big crunch. From that collapse, conditions could reset, igniting a new Big Bang, a new expansion, a new cosmos. Other versions envision even subtler rhythms. In ekpyrotic scenarios, universes are born from collisions of higher dimensional brane, each expansion followed by contraction, each death followed by rebirth. Here, dark energy is not an end but a pulse, a driver of oscillation across cosmic aeons. The cosmos itself becomes less like a line stretching toward oblivion and more like a heartbeat endlessly rising and falling, destroying and recreating. The philosophical contrast is striking. A linear universe, whether ending in heat death or a Big Rip, embodies finality, a story with a last chapter, after which nothing followed. A cyclical universe, by contrast, denies endings altogether. Time itself becomes a circle where every conclusion is also a beginning, every death a seed for resurrection. In such a cosmos, despair gives way to recurrence, and permanence arises not from duration, but from repetition. Yet, cyclic models are not without unease. If universes are endlessly reborn, do they repeat exactly? Are we destined to live these lives again, endlessly in eternal recurrence? Or does each cycle diverge, birthing new possibilities rather than replaying old ones? The tension between repetition and novelty haunts the vision of a reborn cosmos as much as the finality of heat. Death haunts the linear one-dot-still comma. The very possibility is exhilarating. Dark energy, the force that seems to drive us toward isolation or destruction, might instead be the mechanism of renewal. It could be the universe's way of ensuring that endings are never final, that even collapse contains the seeds of creation. In contemplating cycles, we glimpse a universe less like a fading firework and more like a phoenix dying, yes, but only so it may rise again. The terror of the unknowable human beings crave order. From the moment we began charting the stars with stone circles and scratched calendars, we sought patterns to tame the unknown. Newton gave that longing mathematical form. Planets moved in predictable ellipses, forces obeyed elegant laws, and the universe unfolded like clockwork. It was comforting not only because it worked, but because it implied that nature itself was intelligible, a grand mechanism waiting to be mastered. But dark energy shatters that comfort. Here is a force not observed directly, only inferred from the way galaxies flee ever faster into emptiness. It does not fit neatly into Newton's laws, nor even fully into Einstein's. It lurks at the margins of comprehension, a power dominating the universe yet remaining invisible, untouchable, unexplained. Confronted with it, we face the possibility that the cosmos is not fully knowable, that beneath the surface of equations lies chaos, mystery, and silence. This tension is existential as much as scientific. To live in Newton's universe was to inhabit a world of rules, where the mind could, in principle, trace the clockwork of creation. To live in a universe driven by dark energy is to inhabit something more terrifying, a reality whose governing force defies understanding, where acceleration itself feels like the cosmos slipping beyond our grasp. It is not only that we do not know, it is that we may never know. Philosophically, the unknowable unsettles because it resists our deepest habits. We survive by prediction. Harvests follow season. Tides follow moons. Lives follow rhythms. We can anticipate. Mystery can inspire wonder, but too much mystery inspires fear. The fear that we are adrift in chaos. Dark energy embodies that fear on a cosmic scale. It is the reminder that the universe is not obliged to be comprehensible, that our intellect may be dwarfed by forces without analogy. And yet there is paradox here. The same force that terrifies also invites awe. To stand beneath Newtonian order is to feel secure, but also limited, the world reduced to equations, predictable and closed. To stand before cosmic chaos is to glimpse infinity, not safe, not comfortable, but profound. The unknowable strips us of mastery, but in doing so, it grants humility, forcing us to recognize the scale of what lies beyond. In this way, dark energy becomes more than a scientific puzzle. It is a mirror of our condition. We long for order, yet live in a universe that may deny it. We cling to certainty, yet thrive in moments of wonder born from uncertainty. The terror of the unknowable is real, but so too is the strange freedom it offers. To see that mystery is not failure, but the essence of being alive in a cosmos vaster than comprehension. Myths of hidden power. When faced with forces too vast to explain, humanity has always turned to story. Myth is our first language of the unknown, a way to render mystery bearable by giving it shape and name. Dark energy, in its invisibility and dominance, resonates with this ancient impulse. Though couched in mathematics and cosmology, it functions in our imagination like the hidden powers of myth, unseen forces guiding, restraining, or destroying worlds. To compare them is to see how little has changed in the human psyche, even as our tools of explanation have grown. In antiquity, the Greeks spoke of primordial chaos, a yawning void from which all things emerged. From chaos came night and darkness, the shadowed background against which order was established. In Norse mythology, the great void Ginnungagap divided fire and ice, its tensions giving birth to gods and giants. across cultures, hidden forces, sometimes gods, sometimes chaos beings, stood behind the visible shaping creation while remaining inscrutable. Dark energy plays a similar role in modern thought, not a god, but a force invisible and overwhelming, the unseen driver of cosmic acceleration. Even later, as natural philosophy matured, hidden powers remained indispensable. Alchemists and early scientists invoked the ether, a subtle substance thought to fill the void, carrying light and binding the cosmos. It was invisible, undetectable, yet necessary to make sense of motion and transmission. Economists later spoke of the invisible hand to describe forces guiding markets beyond individual intent. Each of these constructs, mythic voids, cosmic ethers, unseen hands, served as placeholders for ignorance, linguistic bridges over gaps in comprehension. Dark energy, named but not known, belongs to this lineage. The contrast, of course, lies in method. Myth accepts mystery as permanent, a truth veiled by gods or fate. Science, by contrast, insists that mystery is temporary, that with time and experiment it can be illuminated. Yet in both cases, the human impulse is the same: to confront the unbearable vastness of the unknown by personifying it, framing it, taming it in language. Dark energy may not wear the face of a god, but it functions as myth nonetheless, a modern chaos that reasserts the universe's strangeness. Philosophically, this parallel is both humbling and liberating. It humbles us because it shows that our vaunted rationalism is not so different from ancient myth-making. When we christen a mystery dark energy, we are doing what ancestors did when they named chaos or Ginnungagap. We translate incomprehension into narrative form, but it also liberates us, reminding us that story is not weakness, it is survival. Myths once helped humans navigate storms and plagues. Today, scientific placeholders help us navigate cosmic enigmas. Both are acts of resilience, ways of living with the unknowable while still seeking to push against it. The danger, as always, is mistaking the story for the truth. The ether was discarded when experiments revealed its absence. The invisible hand proved more metaphor than mechanism. Dark energy, too, may someday vanish, replaced by deeper physics that render it obsolete. In that sense, it may be myth disguised as science, a necessary fiction, bridging us until better understanding arrives. Yet even if it proves illusory, dark energy's mythic resonance endures. It forces us to face the same confrontation as our ancestors, the recognition that the universe is larger than our grasp. Where they spoke of chaos, gods, and cosmic voids, we speak of dark energy and phantom fields. The language differs, but the impulse is unchanged. We seek to name what we cannot. To shape meaning from mystery, to endure awe without collapsing into despair. Our place in the expanding abyss. To contemplate the accelerating universe is to confront a profound disquiet. Our place in a cosmos that is not gathering toward unity but fleeing from itself. Each galaxy that slips further away, each horizon that recedes beyond recovery, is a reminder that the universe is not only vast, but actively stretching into deeper vastness. Against such a backdrop, the human scale, our lifespans, our civilizations, even our species, seems unbearably small. We once believed that meaning could be found in centrality. Ancient cosmologies placed Earth at the center, a stage for divine drama. Even after Copernicus displaced us, we clung to the sense that humanity occupied a privileged position, interpreters of the heavens, masters of the earth, bearers of intelligence in a universe otherwise silent. But dark energy erodes that comfort. It tells us that the cosmos is not only indifferent to us, but moving ever farther beyond our ability to grasp, expanding into a future where isolation becomes the rule and memory itself fades. What does meaning look like in an accelerating abyss? One answer is despair. The recognition that everything we build will be swallowed by entropy, every story extinguished in silence. Yet despair is not the only option. Smallness need not mean insignificance. The very fact that we can recognize our fragility, measure cosmic acceleration, and imagine futures billions of years beyond our own lives is itself astonishing. Against the abyss, consciousness becomes luminous, not trivial, a brief flare of awareness in an otherwise unknowing void. Philosophically, our place in such a universe shifts from mastery to witness. We are not rulers of creation, but observers of its immensity, recorders of mysteries that dwarf us. The galaxies may be racing
away, but in this fleeting moment of cosmic history, we can still see them, still chart their retreat, still marvel at their...
That act of wonder, however temporary, is a defiance of insignificance. It declares that meaning does not require permanence, only presence. In this way, the expanding abyss clarifies rather than destroys. It strips away illusions of cosmic centrality, leaving only the raw fact of existence. We are small, we are transient, but we are here. Our place is not at the center of the universe, but within its story, however brief our chapter may be. And perhaps that is enough. The James Webb and beyond. For all the mystery of dark energy, humanity does not face it empty-handed. Our greatest tool is light itself, gathered by observatories that peer across time and space. The Hubble Space Telescope gave us breathtaking images of galaxies and nebulae, but more importantly, it provided data that sharpened our measurements of expansion. Now, with the James Webb Space Telescope, JWST, our reach extends deeper still into the first few hundred
million years after the Big Bang, toward the moment when the first stars and galaxies ignited.
Each new observatory is a ladder built into the abyss, lifting us closer to understanding what drives the universe apart. The James Webb is uniquely suited for this task. Its mirrors, vast and gold-coated, are tuned to infrared light, the stretched wavelengths of the oldest galaxies and the faintest signals of cosmic history. Already, it has revealed structures more massive and mature than expected at such early times, forcing cosmologists to reconsider how galaxies form and evolve. In studying these ancient objects, Webb also probes the influence of dark energy, the rate at which galaxies cluster, the imprint of cosmic expansion on their distribution, the delicate fingerprints of acceleration embedded in the earliest structures. But Webb is not alone. Ground-based observatories like the Vera Rubin Observatory and the European Extremely Large Telescope promise to map galaxies on unprecedented scales. Space missions, such as the Nancy Grace Roman Telescope and ESA's Euclid satellite, will chart billions of galaxies, tracing the cosmic web with exquisite detail. Together they aim to test whether dark energy is truly constant or if its strength evolves across time, as quintessence or phantom energy theories suggest. These instruments will not detect dark energy directly, nothing we know can, but they will map its effects with sharper precision, tightening the margins where new physics might hide. Yet even with such power, there remains a haunting contrast between what we see and what remains hidden. Telescopes can capture the glow of galaxies across billions of light years, can measure ripples in the cosmic microwave background, can detect gravitational lensing bending the path of light. But they cannot pierce dark energy itself. They reveal only its shadow, its influence on other things. It is like studying the wind by watching trees sway. We know the force is real, but never see it directly. This gap underscores both the triumph and the limitation of modern science. We build instruments of extraordinary sensitivity, expand human vision beyond Earth's atmosphere, and extend our gaze nearly to the dawn of time. Yet the central mystery remains veiled. The better we see, the more sharply we perceive the outline of what we cannot yet grasp. Webb's revelations, like Hubble's before it, remind us that progress is double-edged. Each answer deepens the riddle. Philosophically, this is both humbling and inspiring. To live in an era when our species can send a golden eye into the cosmos, tuned to the faintest whispers of ancient light, is extraordinary. That this eye reveals not certainty but deeper mystery is not failure, but the essence of discovery. The The contrast between what we see and what remains hidden is not a barrier. It is the very horizon of wonder. To the James Webb and its successors will not solve dark energy outright, but they will sharpen its question, drawing the outline of the unknown more clearly than ever before. And in that clarity of mystery lies the real gift, a reminder that we are still explorers in a universe vast enough to defy even our greatest machines. Euclid, Roman, and the hunt for dark energy. If the James Webb Telescope broadens our view of the ancient cosmos, other missions are being built with a narrower but sharper aim: to hunt dark energy itself. The European Space Agency's Euclid mission, launched in 2023, and NASA's forthcoming Nancy Grace Roman Space Telescope are designed not merely to look deeper, but to measure more precisely. Their task is monumental: to map cosmic expansion and structure so thoroughly that theories of dark energy will either be confirmed, refined, or overturned. Euclid approaches the mystery through two main techniques. The first is weak gravitational, lensing the subtle distortion of galaxy shape as their light passes through intervening matter. By measuring these distortions across billions of galaxies, Euclid can chart how matter clumps under gravity, and in turn, how dark energy counteracts that clumping. The second is galaxy clustering, particularly baryon acoustic oscillations, the faint imprints of primordial sound waves frozen into large-scale structure. These patterns serve as cosmic rulers, letting scientists track how expansion has stretched space over billions of years. Together, lensing and clustering promise a map of the cosmos on a scale never before achieved. The Nancy Grace Roman Telescope, expected to launch later this decade, will build on this legacy. With a field of view 100 times greater than Hubble's, it will survey vast swaths of sky in infrared, measuring the brightness and distance of thousands of Type Ia supernovae with unprecedented precision. Like Euclid, it will also trace weak lensing and clustering, creating overlapping data sets that can cross-check one another. Where Webb offers depth, Roman and Euclid offer breadth, assembling a statistical portrait of cosmic acceleration. Here, the contrast between theory and observation sharpened. The LCDM model, with its simple cosmological constant, remains the dominant framework, but cracks in its perfection, like the Hubble tension and hints of cosmic jerks, suggest that reality may be more complex. Euclid and Roman are designed to test whether dark energy is truly constant or if it evolves with time. A discovery of variation would tilt the balance toward quintessence or other dynamic models. Confirmation of constancy would strengthen Einstein's once-abandoned constant. Either outcome reshapes the philosophical weight of dark energy, transforming it from placeholder to principle, or from principle to phase. Yet even these missions confront the paradox at the heart of cosmology. They cannot see dark energy directly. Like all others, they study shadows, inferring the invisible through its influence on the visible. If theory seeks elegant explanations, observation seeks stubborn data. Sometimes the two converge, sometimes they clash. The ether once seemed necessary until experiments dissolved it. Will dark energy endure, or will Euclid and Roman reveal it to be an illusion born of misinterpretation? The answer lies not in equations alone, but in what these observatories record. Philosophically, the hunt reflects humanity's refusal to accept mystery as permanent. We build machines to measure what our eyes cannot, to test whether our stories match the cosmos's truths. Euclid and Roman are monuments to this persistence, vast collaborations of nations, engineers, and scientists, all united by the question of why the universe runs away from itself. Their data will not end the mystery, but they will sharpen it, stripping away easy answers and forcing theory to reckon with reality. In this way, the missions embody the dialogue between imagination and evidence. Theory dreams of elegant constants or exotic fields. Observation demands numbers written in starlight. Between them lies progress, not in the finality of truth, but in the narrowing of uncertainty. The hunt for dark energy is not only about discovering What accelerates the universe? It is about discovering how far human curiosity can reach into the abyss, a revolution waiting in the data. Every great upheaval in science begins with a crack in certainty. Newton's mechanics reigned supreme until Mercury's orbit betrayed a subtle deviation. The ether was assumed essential until experiments showed light needed no medium. Today, dark energy is treated as the silent sovereign of the cosmos, yet its throne is built on inference rather than direct detection. And with missions like Euclid and Roman gathering torrents of data, one must ask, what if the results overturn everything? What if the story of cosmic acceleration is not one of confirmation, but of revolution? Speculation thrives here. Perhaps the data will show that dark energy is not constant but evolving quintessence, shifting across time, reshaping the fate of the universe. Perhaps it will suggest phantom energy, pointing toward the nightmare of a big rip, or perhaps it will reveal something stranger still, that acceleration was an illusion born from cosmic structures, or that gravity itself needs rewriting. In such a case, dark energy would dissolve not into explanation but into correction, like phlogiston and ether before it dot. Imagine the consequences. If dark energy is shown to be an illusion, the cosmological constant, the cornerstone of modern cosmology, would crumble. The LCDM model, long treated as the standard, would fracture. Entire generations of assumptions, equations, and predictions would be called into question. We would stand again at the edge of ignorance, not with despair, but with exhilaration. For revolutions in science do not erase meaning, they expand it, opening new pathways to truth. The possibility of revolution also reflects a deeper truth about science itself. It is provisional. Every constant, every parameter is a placeholder until evidence insists otherwise. To imagine that Euclid or Roman could overturn dark energy is to embrace this humility. The universe is not obliged to match our models. If the data defy us, the fault is not in the cosmos, but in our comprehension. Philosophically, this anticipation is both terrifying and electrifying. Terrifying because it reminds us that our current understanding, however elegant, may be fragile scaffolding. Electrons, atoms, galaxies, all of these once required conceptual revolutions to be grasped. Why should cosmic acceleration be any different? Electrifying because revolution is renewal. To live at the moment when old certainties collapse is to glimpse the future of thought before it is written. We may be on the cusp of ideas as transformative as relativity or quantum mechanics concepts that will reshape not only our science but our sense of existence. And perhaps that is the deepest significance of the hunt for dark energy. It is not merely about solving a puzzle of expansion, but about standing in the liminal space where mystery threatens to become knowledge. The data may confirm what we suspect, or they may break the narrative wide open. Either way, the revolution is not only waiting in the data, it is waiting in us, in our willingness to let go of the comfort of certainty and embrace the unknown. If the results overturn everything, the cosmos will not have betrayed us. It will simply have reminded us of the truth we so often forget, that reality is always stranger, deeper, and more wondrous than the stories we tell about it. Energy, geometry, or something beyond. The very phrase dark energy carries an assumption that what drives the universe's acceleration is a kind of energy, a mysterious force hidden in the vacuum of space. But what if that assumption is wrong? What if the acceleration we observe is not powered by a substance at all, but is instead a feature of geometry itself, or even something beyond our current categories of thought? To ask whether dark energy is misnamed is to question whether we have misunderstood not only a phenomenon, but the very language in which we describe the cosmos. Einstein's general relativity already blurred the line between force and geometry. In Newton's picture, gravity was a force acting across space, pulling masses together. Einstein reimagined it as the curvature of space-time itself, with matter dictating the geometry and geometry dictating the motion of matter. What seemed like a force was really structure. Could dark energy be similar, less a thing filling the void and more a property of the void itself? Some cosmologists suggest that acceleration might arise from the geometry of space-time on large scales. Perhaps the apparent expansion is an emergent effect of averaging over a clumpy universe where voids and filaments bend geometry in subtle ways. Others propose that our equations, when extended to cosmic scales, demand modifications that naturally produce acceleration without invoking a new energy. In such scenarios, what we call dark energy is not a physical entity but a misinterpreted shadow of deeper geometry. Even more radical possibilities exist. Some physicists imagine that the acceleration reflects physics beyond relativity, where our familiar four dimensions are embedded in higher one. In this view, what appears to us as repulsive energy may be the geometric influence of unseen dimensions shaping our observable cosmos. The universe may be accelerating not because of a hidden fuel, but because the stage on which it unfolds is larger, stranger, and more complex than we perceive. The philosophical implications are profound. To name something energy is to place it in a familiar category to domesticate the mystery. Energy is quantifiable, exchangeable, a concept we wield with confidence. But if the acceleration is geometric or arises from principles we cannot yet frame, then dark energy is a misnomer, an attempt to force the unknown into the mold of the known. History warns us of such errors. The ether, once invoked to explain light, was not wrong in spirit. It was an earnest attempt to fill a gap, but it was ultimately revealed as a category mistake. Might dark energy meet the same fate? Still, even misnames serve purpose. They act as placeholders, guiding inquiry until better frameworks emerge. Whether dark energy proves to be a fluid, a field, a geometric twist, or something entirely new, the act of naming it has given us a way to wrestle with the enigma. Science advances not because our first interpretations are correct, but because they are provisional, open to revision. Thus, the question lingers: energy, geometry, or something beyond? Perhaps the universe is reminding us that our categories, force, matter, energy, geometry, are themselves human constructs, useful but limited. The cosmos may demand new language altogether, a revolution of thought as radical as the leap from Newton to Einstein. Until then, dark energy remains both a clue and a confession. A clue that the universe is stranger than we imagined, and a confession that we do not yet know how to name it rightly. The universe, dreaming itself. What if cosmic expansion is not merely a physical process, but something stranger, an expression of the universe becoming aware of itself? It is tempting to think of galaxies racing apart as blind mechanic, equations grinding forward without meaning. Yet when we contemplate the accelerating cosmos, when we give it a name like dark energy, we impose story upon fact, and stories, even scientific ones, are acts of consciousness. Could it be that the universe, in expanding, is also dreaming? Poets and mystics have long imagined the cosmos as alive, its rhythms echoing something greater than mechanism. Ancient myths spoke of world serpents encircling creation, of primordial chaos giving birth to order, of gods whose dreams wove reality. In a way, dark energy resurrects that imagery not as superstition, but as metaphor for a mystery so vast. It resists containment. Expansion is not just matter in motion. It is the unfolding of possibility, the stretching of the stage upon which awareness arises. In this speculative frame, acceleration becomes less a doom and more a gesture of imagination. Just as dreams grow larger and stranger the longer they unfold, so the universe grows more spacious, conjuring new horizons with every passing epoch. Galaxies drift apart like thoughts diverging, each luminous cluster a neuron firing in a mind that spans billions of light years. If consciousness is the cosmos reflecting on itself, then expansion might be the dream continuing, ensuring there is always more to awaken into. But of course, this is not science. in the strict sense. No telescope measures the universe's awareness. No equation encodes its dream. But to reject the metaphor outright is to miss something essential. The fact that we tiny, fragile creatures can contemplate cosmic acceleration is itself part of the dream. Our awareness, born from stardust, is not outside the universe, but inside it. When we reflect on dark energy, the cosmos reflects on itself. The observer and the observed are not separate, but entwined, two facets of a single unfolding dot. The poetry of this vision contrasts starkly with the bleakness of scientific forecasts. Heat death imagines silence, the Big Rip imagines violence, but the dream metaphor imagines continuity. Expansion is not destruction, but transformation, the universe refusing finality, pushing beyond boundaries, insisting on more. If consciousness is the capacity to hold open possibility, then perhaps the universe's expansion is the ultimate act of consciousness, a refusal to close the story. Philosophically, this idea offers both comfort and unease. Comfort, because it rescues the cosmos from being merely mechanical, framing acceleration as an expression of vitality rather than decay. Unease, because it blurs the line between fact and meaning, demanding we accept that our categories, physics and poetry, observation and imagination, are not separate, but overlapping. To say the universe dreams is not to abandon science, but to acknowledge that science alone cannot exhaust the mystery of being. And so we return to awe. Whether dark energy is vacuum energy, geometry, or something beyond, whether it leads to heat death or rebirth, we cannot escape the feeling that the universe is not only expanding, but unfolding into meaning. Perhaps we are that meaning, brief but luminous. Perhaps we are only fragments of a larger dream, or perhaps the truth lies forever beyond us. But in asking, in wondering, in daring to imagine the cosmos as dreaming itself, we participate in the very mystery we seek to understand. A mystery that defines us. Perhaps the greatest gift of dark energy is not what it explains, but what it refuses to. For all our telescopes, equations, and simulations, it remains stubbornly elusive, an unseen presence that governs most of the cosmos while yielding almost nothing of its essence. In this way, dark energy is more than a scientific puzzle. It is a mirror held up to humanity's condition. We are creatures defined not by certainty, but by questions. Other mysteries in science have, in time, yielded to clarity. Electricity, once a curiosity of sparks and amber, became harnessed into the lifeblood of modern civilization. Atoms, once speculative, revealed their structure under the lens of quantum mechanics. Even black holes, once thought paradoxical, are now imaged and studied. Yet dark energy persists in silence, offering no direct detection, no laboratory reproduction, no neat solution. It reminds us that not every unknown is a doorway quickly unlocked. Some are horizons, always receding, daring us to chase. Philosophically, this may be its deeper role. Were the cosmos perfectly transparent to our understanding, wonder would die. A fully explained universe might be efficient, but it would lack mystery, and without mystery, awe withers. Dark energy preserves that awe. It unsettles us, forces us to live with ambiguity, to admit that our grand theories remain incomplete. And in doing so, it keeps alive the restless curiosity that drives both science and spirit. Perhaps, then, the real meaning of dark energy is not its physical nature, but its epistemological power. It teaches humility, that the universe is larger than our grasp. It teaches endurance, that progress comes not from instant answers, but from the patience to question across generations. And it teaches imagination, that when the known fails, we must invent new ways of seeing, new languages of possibility. In the end, dark energy may prove to be vacuum fluctuations, a quirk of geometry, or something stranger still. Or it may vanish as an illusion, a placeholder for misunderstanding. But even if it disappears, the questions it inspired will remain, having shaped how we see ourselves in the cosmos. Its ultimate nature matters less than the fact that it exists as a challenge, a reminder that inquiry is endless, that meaning is made not from answers, but from the pursuit of them. So perhaps the mystery of dark energy does not diminish us. Perhaps it defines us. We are the species that wonders, the beings who look at galaxies rushing into the abyss and dare to ask why. And even if the universe never answers, the act of questioning is itself our greatest gift, the flame of consciousness.
Burning against the dark.